Welcome back. So what we're going to do today is, one, we're going to derive the steady state equations for these two tanks to determine the initial flow rate, and then we're also going to derive the differential equations for the time relation to height of the fluid flowing in and out of both of these tanks. So this is the image. What we have is we have tank 1 with a, I'll use blue here, with an initial fluid height of dependent on time, with radius dependent on time, and then from the center of the tank we have an initial radius, and then we have, I'm going to erase this, I'll put it up for you. And then we have this height from the center to where the fluid is. This is just a 90-degree angle, and this radius. And so what we're going to do is find the flow rate of the fluid from tank 1 into tank 2 through pipe A12 into tank 2. Both of them have fluid flowing in, Qn1, Qn2. Again, height depends on time, or the height of the fluid depends on the time as it flows out of the tank. And so what we're going to do, I'm going to erase this portion of the diagram here for us, so we can solve for the cross-sectional area of this tank, which will come into play later after we solve for the differential height of the fluid in the tanks. So basically, with this, after we have this triangle set up, we have a triangle that is radius, height of the fluid dependent on the radius, minus, erase this, height of the fluid dependent on time, minus r, and then this is radius dependent on time. And so what we're going to do is we're going to say, using the Pythagorean theorem, that r squared is equal to radius dependent on time squared minus height of the fluid at a specific time minus r squared. And then rearranging, we're going to say that the radius dependent on time squared is equal to the radius squared of, or the hypotenuse radius squared of the fluid of the tank itself minus height times height dependent on time minus radius squared. And then, since the tank is a circle, we can say that the cross-sectional area of both of the tanks, since they are both spheres, is pi times radius dependent on time squared, which is equal to pi times the initial radius squared minus height dependent on time, or height minus just the radius squared. So I'll write that over here. We have the cross-sectional area of both of the tanks. Cross-sectional area of both of the tanks is equal to pi times the radius of the tank squared minus the height of the fluid minus the radius squared. Whoa. What is that? Sorry. So we have that. We're going to bring that in later. So after I laid out our problem, what we want to do is, again, find first the initial flow rate of the tanks. And so for the two tanks together, we had that the flow from tank 1 to tank 2 is equal to the connection between the pipe, A12, times the volume of tanks 1 and 2. And we know that flow of tank 2, Q2, is equal to the area of tank 2 times the volume of tank 2. And we need to find volume. And using a similar problem with just regular rectangular tanks at position 1 at a specific pressure and position 2 at a specific pressure with fluid flowing out of the tank, we can say that the pressure 2 minus pressure 1 divided by the density of the fluid in the tanks is plus gravity times position 2 minus position 1. This is negligible though, so we can say that that is equal to 0, plus volume at position 2 squared plus, sorry, not plus, minus volume at position 1 squared divided by 2. Again, this we can say is equal to 0 as well. This whole equation is equal to 0. So then we can say that 0 minus the density of the fluid times gravity times the height of the fluid divided by the density of the fluid plus volume at position 2 squared divided by 2 is equal to 0. Rearranging, we can say that volume is then equal to the square root of 2 times the acceleration due to gravity times the height of the fluid in the tank. So using my blue pen here, volume is equal to the square root of 2 times acceleration due to gravity times height of the fluid in the tank. So from here, we can say that flow from tanks 1 and 2 is equal to the area pipe of the fluid that connects the two times the square root of 2 times acceleration due to gravity, absolute value of the height of tank 1 minus the height of tank 2. And what we need to do is we need to also account for just the flow of the second tank itself. So we need to say that flow 2 is equal to the area of tank 2, or cross-section area of tank 2, times, no, just the area of tank 2, I had to take that back, times the square root of 2 times acceleration due to gravity times the height of the fluid in tank 2. So we'll write those over here. Again, flow from tank 1 to 2 is equal to the connecting pipe that is vaguely still visible up here, if at all. But I can see it. I don't know if you can. Times the square root of 2 times acceleration due to gravity, absolute value of height of tank 1 minus height of the fluid in tank 2. And then the flow out of tank 2, is equal to the area of tank 2, square root of 2 times acceleration due to gravity times the height of the fluid in tank 2. So, if we use mass balance equations, we can say that the flow rate of tank 1 with respect to time is equal to, oh, that's not even a letter. Is equal to Q1 in the flow of fluid into tank 1 minus the flow from tank 1 to tank 2. And we said that Q12 is equal to this, so we can say that the flow rate of tank 1 with respect to time is equal to Q1 in, man, that is really tripping me up. That's a hard thing to write. Flow of fluid into tank 1 minus area 1, 2, square root 2, acceleration due to gravity, absolute value of height 1 minus height 2. And what we need to do here is account for a sign change if height 2 is greater than height 1. So what we say is that the initial flow rate of tank 1 with respect to time is equal to the flow rate Q1 in, there we go, minus the sign compensation for height 1 minus height 2 times the area tank 1, 2, square root of 2 times acceleration due to gravity, absolute value of height 1 of the fluid minus height 2 of the fluid. So again, I'll rewrite that over here. We have that the initial flow rate for tank 1 with respect to time is equal to Q flow rate of tank 1 in, and I really am just struggling to write that. Oh my gosh. In minus sign compensation, again, if the height of the fluid in tank 2 does happen to be greater than the height of the fluid in tank 1. So sign compensation, height 1 minus height 2 times the area of the pipe that connects tank 1 to tank 2 times the square root of 2 times acceleration due to gravity, absolute value, height fluid 1 minus height fluid 2. And so I will erase that, and I guess I'll just write it bigger up here, so that way we have it. So, final answer for the initial flow rate of tank 1. The flow rate of tank 1 with respect to time is equal to the flow of fluid in to tank 1 minus the sign compensation. Again, if the height of fluid in tank 2 is greater than tank 1, which would make it a negative, we change that, make it positive. Height 1 minus height 2 times the connection between tank 1 and 2 times the square root of 2 times acceleration due to gravity, absolute value of height of fluid 1 minus height of fluid 2. So that is the initial flow rate of tank 1. So then we can say that for the flow rate of tank 2, okay. Flow rate of tank 2 respect to time, that is going to be equal to the flow of fluid into tank 2, Qn2, plus the flow from what is between these two tanks, which is Q1, 2, 2. So the flow minus the flow out of tank 2, Q2. So then from here, we can say that this is equal to the flow of fluid into tank 2 plus the area of 1, 2 times the square root of 2 times acceleration due to gravity, absolute value of height of tank 1 minus height of tank 2 minus the area of tank 2 times the square root of 2 times acceleration due to gravity times just the height of tank 2 itself. So again, we need to account for a potential sign change that would arise again if the height of the fluid in tank 2 is greater than the height of the fluid in tank 1. So we say that the initial flow rate of tank 2 with respect to time is equal to the flow of fluid into tank 2 plus the sign compensation of height 1 minus height 2 times the area of 1, 2 times the square root of 2 times acceleration due to gravity times height of fluid 1 minus height of fluid 2, absolute value, minus the area of tank 2 times acceleration due to gravity, or 2 times acceleration due to gravity times the height of the fluid in tank 2. So I will erase all of this, and we will save this equation up top, and then we will solve for the differential height with respect to time in both tanks. So again, for our two tanks, the initial flow rate for the both of them is now written up here. So we have the flow of fluid into tank 2 plus the sign compensation of height 1 minus height 2 times the area of the connector pipe between the two tanks times square root 2 times acceleration due to gravity, absolute value of height 1, or height of the fluid in tank 1 minus height of the fluid in tank 2 minus the area of tank 2 times the square root of 2 times acceleration due to gravity of the fluid in tank 2. So these are our initial flow rate equations. And so now, at the beginning, I said that since we solved for the cross-sectional area, the initial flow rate of the tank with respect to time is equal to the cross-sectional area times the change in height with respect to time in both tanks. And so we want to isolate the change in height with respect to time. It's all we have to do is divide by the cross-sectional area, So that means we get that the change in height with respect to time for either tank is equal to the initial flow rate divided by the cross-sectional area. And so I will rewrite that. This is the answer to part A, we'll call it. Can I use a different marker that might be visible? We'll say that this is A. There's a hole in my board. So that's part A. And so since I will say that again, we know, or we want the differential height with respect to time for a specific tank is equal to the initial flow rate with respect to time divided by the cross-sectional area A cross-section. So, with that being said, since we know that the cross-sectional area is equal to pi times the radius of that triangle that we had, radius, and then we had radius with respect to time, and then height minus the radius. So that's this. So we have the cross-sectional area of the tank is equal to pi times the radius squared of the tank minus this height squared. So, since we have the initial flow rate for tank 1, we can say that the initial, or no, not the initial, the variation of fluid height with respect to time for tank 1 is going to be equal to all of this divided by the cross-sectional area, which I will write out now. So we can say that it is the height, or the flow of fluid into tank 1 minus the sign compensation, line compensation of height 1 minus height 2, or height of the fluids, times the area of pipe that connects it to 1, 2, times the square root, 2 times acceleration due to gravity, absolute value of height 1 minus height 2, divided by the cross-sectional area, which again we already know. So bringing that in, we can say that the differential change in fluid height, or the change in fluid height with respect to time, is equal to the flow of fluid into tank 1 minus the sign compensation if the height of the fluid in tank 2 is greater than the height of fluid in tank 1, times the area of this connector pipe right here, times the square root of 2 times the acceleration due to gravity times the absolute value of the height of the fluid in tank 2, or 1, minus the height of the fluid in tank 1, divided by cross-sectional area of pi times the radius of our tank squared minus the height minus the radius itself, where it is in the tank, squared. So then, simply doing the same thing for the second tank, we can say that the change in time with respect to fluid height, there was change in fluid height with respect to time for tank 2 is equal to the flow of fluid into tank 2 plus the sign compensation, again, if the height of the fluid in tank 2 is greater than height 1, or height of fluid 1 minus height of fluid 2, times the area of the connecting pipe 1, 2, square root 2 times acceleration due to gravity times the absolute value of height of fluid 1 minus height of fluid 2 minus the area of tank 2 times the square root of 2 times acceleration due to gravity times the fluid height in tank 2. All of this divided by cross-sectional area, which again, like we did before, we can bring together, or we can bring in, so that is equal to pi times the radius squared of that triangle that we've drawn now, 3-4 times, minus the height of the fluid in the tank, minus where the length of the radius itself is squared. So this is part B, and that is solving for the variation of fluid height for both tanks with respect to time. So we initially solve for the initial flow rate, or sorry, not initially, but to start, we found the cross-section area of the tank and then found all of the equations that we were going to need to use to get to where we wanted to get, but then we found the initial flow rate of fluid in tank 1 and tank 2, and then using those, we were able to find the height variation of fluid with respect to time in both tanks.
Thank you.